Okay, guys. Good afternoon. My name is Delzy. I'll be your host today. Okay, we're looking at Chem 131. Of course, Chem 131 is General Chemistry 2 for those persons in University of Port Harcourt. Okay. So this for Chapter 1. What you need to know about Chapter 1 and what you'll be doing for Chapter 1 in Chem 131. Chem 131, by the way, is chemical kinetics. Now, the topics listed below are the topics found under chemical kinetics. We have the first topic to be rate of reaction. The second one is Rate's law or order of reaction. The next one is unit of rate constant, integrated order of reactions, half-life and fractional life, effect of temperature on the rate of reaction, calculations and exam-like questions for each topic. It's very important for us to actually solve questions for every single topic we treat. At least that helps us to understand perfectly what we've learned. Okay, so moving further, we have chemical kinetics. Okay, of course, you may want to ask yourself what chemical kinetics is. It's well self-explained here in the materials at the left-hand side of the board. We have the study at which the study of the rate at which a chemical reaction occurs is called the chemical kinetics. Now, what is the major aim of studying chemical kinetics? Of course, it's listed. Now, moving further, we have the outlines for chemical kinetics. The first of them is rate of reaction or reaction rate. Okay, so let's get started. I have Chem 131. For those persons that are used to me, you can testify the fact that I always add a del Z to a particular course I'm teaching. It's more like a trademark. Okay, let's look at rate of reaction. We said rate of reaction can be defined as a change in the concentration of a reactant or a product with time. Okay, first, before we proceed, what are reactants? Now, reactants and products are found in a reaction. Let's say, for example, reaction moving from A to B. Now, every chemical reaction will have this arrow. Of course, this arrow is actually what is differentiating the reactant from the product. The left-hand side of this arrow is a reactant, and the right-hand side of this arrow is a product. In the case of this reaction, the left-hand side is the A. So this A is the reactant, and this B is a product. So this rate of this reaction A to B, I can write the rate of this reaction with respect to A, also with respect to B. Okay, so let's proceed. We said that rate is change in concentration per unit time. So mathematically, we have, let's say, rate with respect to A. All right, this is equals to change. We use D. Now, this square bracket stands for concentration. Okay, now this is divided by change in T. Now, this is mathematical expression of rate. Okay, first, let me actually do this. This mathematical expression of rates. In this case, now there is neither A nor B here. We just say rate is change in concentration per unit time. Now, if I'm now writing this with respect to the reactant, okay, with respect to this reactant, I have minus, I put A here. All right. Now, in this case, now this rate is written in respect to A. Why am I adding the negative this negative sign here? Why am I adding this negative sign here? Because this reactant, this is a reactant, and anytime you're writing rate of a reactant or rate of a reaction in respect to the reactant, we must always indicate or include this negative sign here to show that the reactant is decreasing or is going to disappear with time, okay, for the product to be formed. Okay, so for that of the product, we have rate of B. This is, in this product, we use a symbol of plus. Plus shows that the product will be formed or the product will keep increasing. So this becomes change in concentration of B, which is the product, all over time. So this is the rate of the reaction in respect to B, and this is respect to A. So if I'm to write the overall rate of this reaction, okay, overall rate of the reaction, R equals to negative change in that of A all over the T equals to positive change in that of B. Okay, so with this now, we've actually written the rates of reaction. We've written the rate of this reaction. So all right, so we have this. So if you look at this, we said for every chemical reaction, of course, something moving from a reactant being converted to a product, every chemical reaction will always have this arrow differentiating the reactant from the product. So we write the rate of this reaction in respect to A as negative change in A all over T. This change in A is change in concentration of this A divided by the time. Now rate of reaction in respect to B is positive change in concentration of B respect to time. Now, why is this place negative and why is this place positive? I'll take it again. This place is negative because A is a reactant. Anytime you're writing a rate of a reaction involving a reactant, you must always indicate a negative sign here. Why is it so? Because a reactant always decreases. All right, so this negative sign shows that the guy is decreasing. Now, for positive, for product is always indicated with positive to show that it's actually increasing. Okay, so that is that for the first this. Another thing I would like us to know here is the units of rates of reaction. Now, this is concentration all over time. That's the rates, concentration over time. Now, concentration is always mole per liter and time is always seconds. All right, so this can become mole per liter per second, but do not forget that this mole per liter is same as molar, capital letter M. So we have this. So this can also be the unit of rate of reaction. Okay, so for this first topic, and that is that. Now let's look at the next page. Now there's nothing much to talk about here. Now if you look at this graph actually explains a reaction. Now this same reaction A to B, this A is reactant and this B is product. Now if you look at the start of this reaction, if you look at this graph, at the start of the reaction, the concentration of the reactant was very high because at every commencement, at every reaction, at commencement time, that is as of the time that the reaction is going to start up, there is no product. That is why in this case now the product is drawing out from zero. At the time of the reaction starting, there will be no product and the reactant will be at the maximum. But you realize that as the reaction progresses, right, the reactant decreases and product will start forming. All right, so it simply means that for every chemical reaction, reactant always decreases and product will always increase. That is why we said reactant disappears while products are formed. Okay, moving further. Now, what we have here is actually what I explained in the first slide. We say considering the reaction below A to B, rate of reaction can be expressed in the following ways. Now, for reactants, we use the word disappearance, okay, because reactant will disappear or perhaps will decrease it so that product will be formed. Now, a typical example so that you really understand what I mean by disappearance is in the case of a candle. All right, burning a candle is more like a chemical reaction. All right, the reactant in this case is a candlestick and the product, of course, is the wax that will be formed. Now, before you comment, like at the commencement of the burning, before you light up your candle, you realize that there will be no wax at all. Right, but once you light up your candle, with time, the candlestick decreases, which in this case is a reactant, and product will form. So you realize that after a certain minute, the reactant, which is a candlestick, totally disappears. All right, that means it has decreased to the point that the candlestick no longer is in existence, it disappears, and the evidence of that will be seen in the formation of the wax. All right, so that is why we say for reactant we always use disappearance for reactant or decomposition. All right, so in this case now the reactant is A, and of course that is why we have a negative sign here. I already explained that in the first slide. Now for product is appearance or formation. So rate of reaction with respect to B is called rate of appearance. Of course, I already explained this. Now I state the negative sign in the rate of disappearance signifies that the reactant is decreasing while the product is increasing. So if you look at this, actually gave us the overall rate of the reaction. Okay, now let's look at average rate of reaction. Now when we say average, we're actually looking at a time interval. For instance, we have time 1 and time 2. Right, so based on what is written here, we say that average rate of reaction is a change in reactant or product concentration over a given time interval. Right, so the formula is actually self-explanatory. Now if you look at this, we say for average rate of reaction, now this becomes change in concentration all over change in time. Now if you're writing average rate of reaction, this sign now, this change is more like the final and the initial. This average, the first one we did was instantaneous or instant, right? So this average rate of reaction is basically the rate of a reaction over a given time interval, right? Now if you're writing average rate of reaction for a reactant, let's say for a reaction moving from A to B, now average rate of A, in this case is a reactant, all right, is going to be concentration of A at time 2 minus concentration of A at time 1 divided by T2 minus T1. Now do not forget that A is a reactant, and because of that you must attach a negative sign here to show that reactant decreases. This negative sign must be attached regardless of whether or not you're writing the average or you're writing instant rate of reaction. Okay, now for the B, for we say average rate of B. B is actually the product, so we have to put plus. So this becomes concentration. This square bracket stands for concentration at time t at the final. That's, remember I told us that average is written for 2 time interval, the initial time and the final time. The final time is this at the second condition, which is 2. The initial is at the 1. So this becomes concentration at 2 time 2 and concentration at time t1. Now this is divided by T2 minus T1. So basically this is what average rate of reaction is all about. Now for those persons that might want me to recap this again, average rate of reaction is basically the rate of a reaction over a given time interval. Let's say 2 time interval, time t equals to 10 seconds and time t equals to 50 seconds. So we have 10 seconds and 50. So they are asking us what is the average rate of reaction between these 2 time interval. The initial time interval is actually 10 seconds and the final is 50 seconds. So we take the 10 seconds to be initial condition and the 50 seconds to be final condition. So for us to get the average rate, if it were to be a reactant, you must attach a negative sign to show that it's a reactant. And after which, for the product, for the concentration, you're going to say concentration of the reactant at the final time, concentration of the this in at the initial time divided by the final time minus initial. All right, same thing is applicable to the product. All right, product is going to be concentration of the product at the final time minus concentration of the product at the initial time divided by the final time minus initial time. Okay, whatever the answer gives you becomes that. Of course, at the end of this session, we're going to take some few examples. All right, so or after now, we're going to take an example for this. Now, there's another thing I would like to explain. reaction rate and stoichiometry. If you notice, all the reaction, the two reactions are given to us. The first reaction I gave us A plus B. Sorry, I gave us A. Give us A into B. If you notice, this reaction do not have any stoichiometric coefficient. This reaction do not have stoichiometric coefficient. Now, what if for reaction with stoichiometry coefficient? Let's say example, we have A okay, let's just take one. We have A giving us B. If you look at this reaction here, there is a coefficient here. Now this A is a coefficient and this B is a coefficient of this guy. So in this case now, there was no coefficient, so it was assumed to be, it was 1 actually. But this A could be something else other than 1. It could be 2, it could be 3. If it is 1, it doesn't really matter because 1, of course, is same. 1 multiplied by anything is still the same stuff. So in this case now, if I'm writing rates of reaction with respect to A here, in this case, it's simply going to be minus, because A is a reactant side, 1 all over the coefficient. Right, in this case, since there is a coefficient here, it's going to be reciprocal of the coefficient, 1 all over A. Now we have change in A divided by dt. All right, now for B, it's going to be plus, because B is on the product side, 1 over B, reciprocal of this, change in this all over T. All right, so the overall rate of this reaction becomes, minus 1 over A change in A equals to plus 1 over B change in B. So in this case now, anytime you're given a reaction that has a coefficient and you're asked to give how will I put it in a reaction rate for that guy, it's very simple. Let's take a typical example. Let me just clean up this a bit. Let's take example. I'll say example, if I have something like this, I have example, we have 2A. If we look at the question, the problem exercise from the material at the left hand side of the screen, you see where we have, you say, which of the following rate expression is incorrect? Now this is the rate of this is the reaction. The action also give the rate of this reaction. Now if you look at this, let's get rid of all of this. If you look at this now, you can tell that this is actually a coefficient. This is a coefficient, is not 1, this is not 1, so this coefficient are different. So you come here, you say the rate of this overall reaction. We are going for the overall reaction, so we say our rate of the overall reaction. A is a reactant, the coefficient in front of A is 2, so because A is a reactant, I'll start with a negative. Now 1 over 2, because remember, anytime you're writing rates for a reaction that has a coefficient, is going to be reciprocal of that coefficient, then you proceed. So 1 over 2, this 2 is a coefficient here, then change in A all over dt. This is equals to, regardless of the fact that there is a plus here, you don't use plus here, you see how put it equals to, because the rate of this must equal to the rate of this must equal to the rate of this. So it's going to be equals to, B is also on the reactant side, so I use negative, and B has a coefficient of 3, so it's going to be reciprocal of 3, which is 1 over 3 dB all over dt. Now equals to, C is on the product side, so I use plus the 1 over 4 the C. Now, if you look at the options, if you look at the options, look at option A, option B. Now, if you look at this question, they did not really give us, the option E would have actually been correct. But if you look at this option E, on the product side, C is on the product, so this minus is not supposed to be here. All right, so because of this guy here, because of this is wrong. All right, so I would say because of this, that option is wrong. All right, now if you look at option A is actually correct. Remember, this is equals to this is equals to this, so just this alone, if you insert this alone, you can get this R. All right, so most of the times they might not give us this entire expression, they can just give us any one of these, or they can combine two of them. But remember that since this is equals to whatever I have here, if I equate it, is going to give me whatever I have here, and it's going to give me whatever I have here, which of course is going to give us this R. So most of the time they can just pick up one of these as an option, or they could just combine both of them. So if you look at the A option, this is minus 1 over 2 dA over dt. Okay, this is correct. All right, they said which of the following is incorrect. Oh, that was the question, which of the following is incorrect. Okay, so this is correct. Okay, so we go, this is correct. Now if you look at the B, if you look at the B part, this is minus 1 over 3 dB, and if you look at B is minus 1 over 3 dB over dt. So this B is correct as well. All right, now if you look at C, all right, C here is actually, this place is meant to be C, it's meant to be C, it's not meant to be 4. All right, so you could just correct that, it's meant to be C here, the C, not the 4. So if you look at this, C is actually plus 1 over 4 plus, so this is meant to be correct. This is correct. Now if you look at the D, they are combining two in this case, they are combining the A and the B, and if you look at this is minus 1 over 2 the A over the T equals to minus 1 over 3 dB. So this is actually also very correct. So you realize that the one that is not correct is this E. And why is E not correct? If you look at the expression, all of this would have been correct, but the problem here is that they are giving C a negative sign, which is not true because C is on the product side class. All right, so that is why this option is wrong. Okay, I believe we have actually understood how to do this. All right, so what if they gave us something like this? They said example 2, we have H2 3H2 plus N2 giving us 2NH3, and you have to write the rate of this reaction. So this is going to be rate equals to H2 is actually the reactant side, so this becomes minus 1 over 3. The coefficient is 3, so it's reciprocal. Change in H2 all over the T. Remember, this plus, you're not going to put plus, but equals to, because the rate of this is going to equal to this and equal to this. So this plus, you don't actually indicate it. So this becomes minus, there is no coefficient here, so it's more like saying 1 over 1. There is 1 here actually, so it's more like saying 1 over 1, which of course is the same thing as not writing anything here at all. All right, so this becomes equals to minus change in N2 all over the T equals to. Now if you move down to the product side, now the product is actually going to be a plus. All right, so this is 1 over 2 change in ammonia. So that is it. Okay, so that is actually that for this. All right, so let's proceed. It's almost, you see the same thing. So you could just attempt this. You could pause the screen, you could pause the video and attempt to get the answer to this question. Okay, so if you look at this, when I talked about average rate of reaction, all right, so we said average rate of reaction is actually rate of reaction over a time interval. So in this case now they said calculate the average rate of reaction between 400 and 600 seconds. All right, so at 400 seconds we have concentration of 1.28, and 600 we have this. Of course, we're going to say the smaller value becomes initial, and the larger value becomes the final. So you notice the concentration at the initial time was 1.28, and the concentration at the final time is 1.25. So basically, this is going to be, you say, average. Sorry about that. We say average rate of reaction is going to be concentration at the final time, concentration at the initial time, all divided by final time minus initial. Now T1, they gave us to be 400 seconds. T2, they gave us to be 600 seconds. Now concentration at T1, concentration at T1 is equals to 1.28. Now concentration at T2 equals to 1.15. Now, for the fact that they said the composition of N2O5, for the fact that they said the composition, it simply means that N2O5 is a reactant. Do you understand me? N2O5 is a reactant, so this is going to be equals to, I use a negative sign because they said the composition. Now, they said the composition. Product does not decompose. Product is formed, right, or produced. Reactant decomposes or disappears. All right, so because it said decomposition, that gives us an idea that this particular substance is a reactant. So this becomes concentration at final time minus concentration at initial time all over T2 minus T1. Now, you put your negative here. Concentration at the final times is actually 1.15 minus the other one is 1.28. Sorry. So we have 1.28. This is divided by, we have T2, we have 600. So we now have our average rate to be equals to, we actually evaluate that you're going to have 6.5 times 10 raised to the power of 4. Now, this is mole per liter per second. Okay, so if you actually follow, please give us a thumbs up, and then please do well to like our YouTube channel. Delzy Scholars. Thank you.